Hi, my name is Nuraz Bastafrina bin Himat Zairi. I will present the first part of this video. For question, figure shows a coilover shock absorber. The coilover is a suspension device that is widely used in automobiles. The coilover consists of two main parts that are a damper and a coil spring. In the coilover, the damper is situated at the center of the coil spring. The oscillation of the coilover on a bumpy road can be expressed by a second-order ordinary differential equation, or ODE. The retarding force due to the damper must be included in the ODE. You can assume that the spring length is equal to the equilibrium length of the spring in the aperture condition. This means that the weight of the automobile is ignored through this assumption. Next, for a function of each part of coilover shock absorber, first is the coil spring. It supports the vehicle's weight and absorbs impacts from bumps. The second one is shock absorber or damper. It controls the spring movement, preventing excessive bouncing. Third one is adjusting collar. It allows the ride height to be raised or lowered. The fourth is mount. It connects the coilover to the vehicle, suspension, and chassis. For part 1, the derivation of our ODE and its solution, we set up the equation and we get mx double prime plus cx prime plus kx equals to 0. Next, by dividing the m, and we define that U gamma equals to c over m and omega naught squared is k over m, and solve via characteristic equation by assuming x equals to exponential rt and substitute it in, we get r squared plus 2 gamma r plus omega naught squared equals to 0, and the roots is r equals to negative gamma plus minus square root gamma squared minus omega naught squared. Next, shows the 4 cases: undamped, underdamped, critically damped, and overdamped. Using 3 decimal places as required, these are the values and the damping values chosen. For first case, undamped condition, we get xt equals to 1 cos 2.719 t. For case 2, the underdamped condition, we get xt equals to exponential negative 1.581 t times 1 cos 2.212 t plus 0.715 sin 2.212 t. For case 3, critically damped condition, we get xt equals to 1 plus 2.719 t exponential negative 2.719 t. For case 4, the overdamped condition, we get xt equals 1.159 e to the negative 1.007 t minus 0.159 e to the negative 7.341 t.
I'm Ivan. Now I will talk about the graph behavior for 4 of these damping cases. First, for the blue undamped curve, it shapes into a permanent and perfect cosine wave because there is zero resistance in the system, so no energy is lost. It fluctuates infinitely between 1 and negative 1 meters, meaning the car would bounce forever without stopping. Next, for the green underdamped curve, it shapes into a decaying wave. It has a low damping resistance which allows the system to cross the zero equilibrium line, which causes the overshoot and a few structural bounces. However, the amplitude is squeezed over time by an exponential envelope until it gradually settles to 0. Third, for the critically damped curve, which is purple, forms a smooth and rapid decay shape to 0. This specific shape happens because the damping resistance is perfectly balanced. It forces the system back to equilibrium in the absolute fastest time possible without overshooting the baseline or bouncing even once. This represents the ideal suspension setup. Finally, for the black overdamped curve, it shapes into a flat and sluggish tail because the suspension is excessively stiff. The fluid resistance is too high. It successfully prevents any bouncing, but it resists movement so heavily that it creeps back to equilibrium much lower than the critical case.
For discussion of the graph, we can see that there is 4 cases, which is the undamped case, which is c equal to 0. So the system oscillates constantly at omega equal to 2.719 radian per second, with no decay at all, because there is nothing to dissipate the energy. For the undamped case, which is c equal to 3.162, the oscillations still happen, but now they decay exponentially, breaking in flight to the negative 1.581 t. You can see this on our graph, which is the green curve, keep bouncing but each peak gets smaller. For the critical damping, which is c equal to 5.438, something interesting happened, which is omega equal to gamma. Exactly, the roots become real and repeated, and oscillation disappear completely, which is the fastest possible return to equilibrium without overshooting, which is the ideal cases. For the overdamped case, which is c equal to 8.347, the omega is now greater than the gamma is greater than omega. The roots are still real but distinct, so again there is no oscillation. However, it returns to the equilibrium more slowly and sluggish than the critical case. In real world context, if the coilover were undamped, it would be generally dangerous because the car will keep bouncing after every bump using the target traction. For undamped setup, you will find the standard consumer car, which is a few gentle bounces that settle up quickly, that give a balancing comfort and control. For critical damping, it will give a maximum stability and tire contact immediately after a bump, which is why it is used in high performance racing setup. For overdamp cases, it will use in heavy-duty vehicles such as trucks that carry the heavy loads to prevent the bottoming out. So, this trade-off right comfort that making it feel stiff in regular passenger car. This assignment derived the coil-over governing, which is ODE, from the Newton's second law and solve it analytically for all damping cases. Using rational constant, which is omega equal to 2.71 radian per second, verify the analytical and simulated result. The results show damping controls whether the system oscillate or settle smoothly, with critical damping returning to equilibrium faster without overshoot. In real world, manufacturers choose the undamped setup for comfort and overdamped setup for load stability, showing this single ODE directly govern real world ride quality and safety.